4.3 Monotonic functions and the first derivative test. The outline of this video is as follows. We will begin by discussing how to use the sign of the first derivative to determine precisely where a function is increasing, meaning its graph is rising, and where it is decreasing, meaning its graph is falling. This is a fundamental skill for understanding the overall shape of a function. Then, I will introduce a powerful and intuitive tool called the first derivative test. This test leverages our knowledge about increasing and decreasing intervals to systematically find a function's local extrema, which are the local maximum and minimum values, or the peaks and valleys on the graph. To make sure these ideas are perfectly clear, we will then apply this entire procedure to several worked examples, moving from theory to practical application. By the end, you will have a reliable method for analyzing any function's behavior. Let us begin by building a solid intuition for what it means for a function to be increasing or decreasing. Visually, a function is increasing on an interval if its graph goes uphill as you move from left to right, like walking up a gentle slope. Conversely, a function is decreasing if its graph goes downhill. If a function exhibits one of these behaviors consistently over a stretch of its domain, we say it is monotonic on that interval. It is important to remember that these are properties over an entire interval, not at a single point. While looking at a graph is helpful, we need a more precise and analytical method. This leads us to the central question we will answer. How can we use the derivative to tell us exactly where a function is rising or falling? Answering this will give us a powerful tool for analyzing a function's behavior without ever needing to see its graph. We can now use the sign of the first derivative to determine precisely where a function is increasing or decreasing, which is a direct application of the mean value theorem. This theorem tells us that the change in a function's value, which is f of x2 minus f of x1, is equal to the derivative at some point c times the quantity x2 minus x1. Because we always look at an interval from a smaller x1 to a larger x2, the term x2 minus x1 is always positive. This means the sign of the function's change depends entirely on the sign of the derivative, f prime of c. If f prime is positive across an interval, the function's value must rise, so the function is increasing, like walking uphill. If f prime is negative, the function's value must fall, and the function is decreasing. The simple takeaway is that a positive derivative means the function is going up, and a negative derivative means it is going down. Now I will outline a reliable procedure for determining the intervals where a function is monotonic, which simply means where it is either increasing or decreasing. First, we find all the critical points by calculating the derivative and identifying where it equals 0 or is undefined. These are the only places where the function's direction can change. These critical points then partition the function's domain into a set of distinct, open intervals. Next, we can pick any single test point within each interval and evaluate the sign of the derivative there. Finally, we apply our corollary. If the derivative at our test point is positive, the function is increasing on that entire interval, and if it is negative, the function is decreasing. For example, if the derivative is positive in the interval from 2 to 5, we know the function is rising across that whole stretch. The key takeaway is that the sign of the first derivative between critical points tells us the function's direction. Let us apply our method to find where the function f of x equals x cubed minus 12, x minus 5 is increasing or decreasing. First, we compute the derivative, which is f prime of x equals 3x squared minus 12. We find the critical points by setting this derivative to 0, which gives us solutions at x equals -2 and x equals +2. These 2 points divide the number line into 3 open intervals, from -infinity to -2, from -2 to 2, and from 2 to infinity. To determine the function's behavior, we test the sign of the derivative in each interval. For instance, if we test x equals 0 in the middle interval, the derivative is -12, which tells us the function is decreasing there. Testing the outer intervals reveals a positive derivative, so the function is increasing on those. Remember, we always check the sign of the derivative, not the original function. Therefore, the function increases, then decreases, and finally increases again. This graph gives us a clear picture of what we mean when we say a function is increasing or decreasing on an interval. Visually, a function is increasing if its graph moves uphill as you trace it from left to right, and decreasing if it moves downhill. Following this particular curve, we can see it rises for all x values up to -2, so it is increasing on the interval from -∞ to -2. Then, between x equals -2 and x equals +2, the graph falls, which is an interval of decrease. Finally, for all x values greater than 2, the graph rises again, making the function increasing on the interval from 2 to infinity. At points where the behavior changes, at x equals -2 and x equals 2, are our critical points. By simply looking at the graph, we can identify where the function rises and falls. We can now use the sign of the first derivative to find local maximums and minimums with a powerful tool called the first derivative test. This test works by looking at how the sign of the derivative, f prime, behaves as we move across a critical point, which we will call circa. If f prime changes from negative to positive at c, it means the function was decreasing and then starts increasing, which creates a valley shape, giving us a local minimum. On the other hand, if phi prime changes from positive to negative, the function was increasing and then starts decreasing, forming a peak, which is a local maximum. Be careful, because if f prime does not change sign at all, for instance staying positive on both sides of ski, then there is no local extremum there. The function simply pauses before continuing in the same direction. The essential idea is that a sign change in the first derivative at a critical point reveals a local extreme ecium. We can now use the sign of the derivative to classify our critical points as local maximums, minimums, or neither. This is the core idea of the first derivative test. Imagine we are at a critical point of a continuous function. If the derivative f prime changes from positive on the left to negative on the right, it means the function was increasing and then switched to decreasing, creating a local maximum, like the top of a hill. On the other hand, if f prime changes from negative to positive, the function was decreasing and then began increasing, forming a local minimum, like the bottom of a valley. It is also possible for the sign of the derivative to be the same on both sides. If f prime is positive on both sides, for example, the function simply pauses before continuing to increase, so there is no extremum. Therefore, a local extremum exists at a critical point only when the first derivative changes its sign. Now let us analyze a function where the critical points come from two different sources, which is a very common scenario. Our function is f of x equals x to the power of 1/3 times the quantity x minus 4. After we find its derivative and simplify, we get f prime of x equals the fraction, with 4 times the quantity x minus 1 in the numerator, over 3 times x to the power of 2/3 in the denominator. To find the critical points, we look for where this derivative is either 0 or undefined. The derivative is 0 when its numerator is 0, which gives us x equals 1. It is undefined when its denominator is 0, which gives us x equals 0. Do not forget to check for both conditions. These two critical points partition the number line, so we can now test the sign of the derivative in the resulting intervals. For instance, on the interval from 1 to infinity, the derivative is positive, so the function is increasing there. The key lesson is that critical points can occur where the tangent is horizontal or where it is vertical. Now I will use our sign analysis to classify the two critical points we found. First, let us look at x equals 0. Since the derivative is negative on both sides of this point, its sign does not change, which tells us there is no local extremum here. In fact, because the derivative is undefined at x equals 0, the graph has a vertical tangent at the origin. Next, at x equals 1, the derivative's sign changes from negative to positive. According to the first derivative test, this indicates a local minimum. We can find the value of this minimum by calculating f of 1, which is 1 times the quantity 1 minus 4, or negative 3. Because the function decreases everywhere before this point and increases everywhere after, this local minimum is also the absolute minimum value of the function. So remember that a critical point is only a local extremum if the derivative changes sign there. Now let us analyze a function that is a product of a polynomial and an exponential term, which is a common pattern you will see. To find the critical points, we first need to find the derivative using the product rule. This means we take the first part, the quantity x squared minus 3, times the derivative of e to the x, and add the second part, e to the x, times the derivative of x squared minus 3. After simplifying and factoring out the common e to the x term, our derivative becomes the quantity x squared plus 2x minus 3, all times e to the x. To find where this derivative is 0, we can use a helpful fact. The exponential function e to the x is always positive and is never 0. Therefore, we only need to find where the polynomial factor equals 0. Factoring that quadratic gives us the quantity x plus 3 times the quantity x minus 1, which means our critical points are at x equals negative 3 and x equals 1. Let us use the sign of our derivative, which is the quantity x plus 3 times the quantity x minus 1, all times e to the power of x, to find where the function increases and decreases. Since e to the power of x is always positive, we only need to look at the signs of the other two factors. For x less than negative 3, the derivative is positive, so the function is increasing. On the interval between negative 3 and 1, the derivative is negative, so the function is decreasing. And for x greater than 1, the derivative becomes positive again, making the function increase. Applying the first derivative test, we see that at x equals negative 3, the derivative's sign change from positive to negative reveals a local maximum. Conversely, at x equals 1, the change from negative to positive reveals a local minimum. So by analyzing these intervals, we have located the function's extreme values. Let us summarize the powerful connection between a function's first derivative and its shape, which is the key to finding local maxima and minima. The core principle is that the sign of the first derivative, f prime of x, tells us the direction of the original function. If f prime is positive on an interval, the function f is increasing, and if f prime is negative, the function is decreasing. This relationship makes certain points especially important. We call the points where the derivative is either 0 or undefined the critical points, because these are the only places where the function can change from increasing to decreasing. The first derivative test is our tool for classifying these points. By checking how the sign of the derivative changes as we cross a critical point, we can determine if it is a local maximum, a local minimum, or neither. For instance, if the derivative changes from positive to negative, the function went from increasing to decreasing, forming a local maximum like the peak of a hill. So the first derivative provides a complete roadmap to find and classify the peaks and valleys of a function. To finish, let us use these questions to review the connection between the first derivative and the shape of a function. The key idea is that a critical point signals a potential local extremum but does not guarantee one. For the first question, where f prime of x equals the quantity x minus 5 squared times the quantity x plus 1, The critical points are at x equals 5 and x equals -1. Because the x minus 5 squared term is always non-negative, the sign of the derivative depends only on the x plus 1 terms. The function is therefore increasing when x is greater than -1. This leads us to the second question. At x equals 5, the derivative is 0 but does not change sign, so there is no local extremum. The graph might have a horizontal tangent at a point of inflection. Remember, a local extremum in Neelam requires the first derivative to change its sign at the critical point.